Welcome back. Hope you're doing well. Today we begin our discussion of abstract vector spaces, although we've touched on it briefly before. But we wanted to be discussing norms and inner products, the type of Euclidean structure that you could be putting in specific vector spaces. Now, not all vector spaces have norms and inner product, and some vector spaces, as we will see, have multiple different norms and multiple different inner products that we could be going through and defining. But we want to make sure that we discuss these definitions here first so that we know what we're working with. Oftentimes in the future, we will want to say we were working in a normed vector space, and that will mean we want a notion of length for that vector space. We will want a notion of what it means for a vector to have a distance to it going from 0 to it. But we won't even be thinking about these things in terms of distance, although, like we were mentioning in our previous videos, distance does come from this notion of norm, because we're just asking for every vector to be assigned a specific function. Let's take a look at what that function is for the norm. Now, the notion of norm is generalizing this notion of length for Rn. Let's let V be a general vector space. Here we have a vector field F, where F is the real numbers or the complex numbers. Those are the two ones that we've been talking about so far, and also the fields that most commonly have norms associated to them. We're going to call a function alpha from V to the real numbers, regardless of the field that you choose here. Your norm is always going to be a real number if it has the following properties. Look at this and tell me what's different from the notion of this function that we had before. There shouldn't be much, if any at all, because we said that for our length there, we had to have that the norm of x was greater than or equal to 0 and only equal to 0 if our vector was equal to 0. And then scalars come out, but they have absolute values by them. And then finally, the subadditivity, which we still call the triangle inequality. So these three names, positivity, homogeneity, and triangle inequality, all still carry over. In fact, whenever we're talking in terms of a general vector space, we will usually denote the norm much like this. I have seen in the literature some people writing norms like this, but we are going to add the double bar here because what we are trying to distinguish this from is things like this absolute value in the real numbers. In the real numbers, we want to keep the absolute value meaning the same. So we're going to distinguish the norm to be something with regards to a vector field. So whenever we have a single bar around of this right-hand side of here should be a real number or perhaps a complex number, right? So real or complex. And then the double bars are going to mean that this is a vector inside of here. So this is a property that belongs to vectors. Now, sometimes for a vector space, like we were mentioning before, you can have different norms. So sometimes what we'll do is say I'll have a norm sub 1 and a norm sub 2. So this is going to be two different norms happening on the same vector space. And the way we'll distinguish them is with little subscripts down here. So here is that definition, this time with the norms back in there. Now it looks a lot like what we had in the space of Rn. And we'll say that a norm vector space is a vector space that has a norm on it, and namely a norm that satisfies all three of these properties. We can't just slap a real number on everything and say this is a norm. It has to be satisfying these three properties. So we'll need to be careful on some certain things when we're asked, is this a norm, to make sure that this actually satisfies these three properties. The reason we wanted to satisfy these three properties is that we're attempting to emulate the notion of length in the real numbers so that it works well in any other vector space that we're working with. So we want to make sure that length is always something non-negative and only 0 when we're measuring 0. We want to make sure that length is scalable. And finally, we want to make sure that triangles work nicely in our space, namely that the length of the third side is less than or equal to the sum of the other two. So that is where triangle inequality comes in. With these three conditions together, we start getting something called a norm. Now, the norm defines a distance as well, just like in the same way that we saw it with Rn. If you want to find the distance between x and y, it's the same as just taking the norm of the difference between the two vectors. Let's start by looking at different norms in the vector space that we're familiar with, namely in Rn. We know this one. We know the norm that goes like this. We have the norm of the vector x, which is this in terms of, and I'll put a subscript here later. We know that this norm is going to be x of 1 squared plus x of 2 squared plus ... plus x of n squared. This is the Euclidean norm, is another way to call it. The Euclidean norm because we're using Euclidean distance in order to define it, right? This is the Pythagorean theorem and things like this. But what if we didn't measure distance that way? What if we measure the distance of the vector 1, 2 by measuring simply the largest value inside of my vector? What if the norm of this was 2? Well, I could go through and check to see if this ends up being a valid form of distance. And we'll show in this slide that it does. And we're going to call this the infinity norm of a vector. The infinity norm is going to be the max of the absolute values of all components of our vectors inside of Rn. First things first, is it positive? You better believe it is, because you're taking the maximum of absolute values of things. And is it 0 only when the vector x is 0? Well, if I had anything non-zero in any of my components, the max part would pick it up. So we know that this also gives us that part of positivity. Homogeneity, if you scale every vector by the vector by r, then every single component inside of here will scale by r as well. And so that means that we could just bring the r outside. So it's going to be the magnitude of r times the maximum of each of the individual ones. So that gives us homogeneity. Now we want to show the triangle inequality. This one's going to take a little bit of just thinking about what the maximum means for these sorts of things. We know that for each component of the magnitude, or yes, exactly. So for each component, if we measure the magnitude of x sub I plus y sub I, which would be the ith component of this vector, x plus y, then that would be less than or equal to, by the triangle inequality for the real numbers, the magnitude of xi, or the absolute value of xi plus the absolute value of yi. Well, then at this point, we can absolutely say that this x sub I is less than or equal to the max of all of the x sub i's put together, and that this particular magnitude of y sub i's is less than or equal to the max of the y sub j's, with j is ranging over every single element inside of our thing. Well, if this is true for any particular I, which this is true for all I inside of our set going from 1 to n, then we can just go through and take a maximum. Is because this is true for every single one. So whichever one is the biggest one also has the same statement being true. Whichever one is the biggest of all of these i's has the same thing being true, because this was true for all I. Well, this is the infinity norm of x plus y. This is the infinity norm of x. This is the infinity norm of y. So that gives us the triangle inequality for this. So this is the infinity norm. We've shown that this does work. The infinity norm, taking a vector like 1, 2, and just popping out the number 2. That is an example of using the infinity norm. What that means is that the notions of length that we're familiar with on a kind of a structural level are all retained in this vector space, even when we talk about norm vector space with this norm right here. It's not the same definition. It's not true that every single vector has the exact same length as before, but structurally, there's a lot of similarity between them. Let's take a look at another norm. So we've seen what is known as, we've seen the Euclidean norm, we've seen the infinity norm. Here's one called the one norm. What if we didn't take the square root of the square of each element? What if we just took the absolute value of x1, added it to the absolute value of x2, and all the way up to the absolute value of xn? Would this be a norm? Well, very nicely, the triangle inequality works out very nicely here, because each component is just going to break up, thanks to the triangle inequality, for the real numbers into the magnitude of xi plus the magnitude of yi, and then you can just sum all of those together. Remember that, noticing that this is a sum here, I get that the left-hand side is going to be the sum of, is going to be the one norm of x plus y, and then that the right-hand side here is going to be the one norm of x plus the one norm of y. So this is the example of something called the one norm, where you sum all of the components here. So for example, the magnitude or the norm of 1/2 here with respect to the one norm would just be 1/2 plus 1/2. This would be something of distance 1, quote unquote, from 0. This would be something of norm 1 in this space, in this norm vector space. And it doesn't look like it does. In fact, I feel like if I had to do this normally, I'd have to go through and do a triangle inequality, get that this element is actually of Euclidean length, 1 over square root of 2. But that's what it is in the Euclidean norm. What it is inside of the one norm is a different length entirely. Okay? By the way, sometimes we'll be calling this one the 2 norm. The reason we're going to see for that reason for it in a little bit, but you can kind of surmise that it's from the fact that we are squaring a bunch of things and then we are taking a square root. So there is a notion of 2 going on here, whereas here it's kind of more of a notion of 1. There's no square root at all, but everything is raised to the power of 1. So there's some sort of connectedness between these things. In fact, we can do the same structure, but this time for a general value of p, the norm of p, where p, we can define this where p is greater than 0, but it's not going to be a norm for all p greater than 0. But we could define this if we would like. We could define it to be the magnitude of x1 to the p plus x2 to the p plus all the way to the magnitude of xn to the p. But then we have to take the pth root once we're done. So for example, like we see here in the remark, the norm of x2 is the Euclidean length of x. The theorem is that this is a norm for any p greater than or equal to 1. In between 0 and 1, it's something known as a semi-norm, but for p greater than or equal to 1, it does satisfy the triangle inequality, right? The triangle inequality for p greater or equal to 1 is known as the Minkowski inequality, and it works a little bit like this. You can see here that this is a way of splitting things up based off of where you're looking at x plus y right here, and then here where you're looking at x, and here you're looking at y. So this is that inequality there. So norm vector spaces are these vector spaces endowed with a norm. They get us a distance by just saying, okay, we can take a distance between two vectors by taking their difference and then taking the norm of the resulting vector. We also have a notion of convergence here. Now we're coming back to the notion of convergence inside of a vector field. But when we say convergence here, we're not saying convergence in the sense of for all epsilon, there exists a delta and things like this. That is for a specific norm that converges. For this one, we are saying that if we take the distance function first and then go back into the real numbers and say, okay, how do things converge in the real numbers? Now we're looking at for all epsilon, there exists an n and things like this. Now we have this notion of convergence here. The reason that I want to specify that is that sometimes you could ask the question, okay, what happens if I take the vectors x sub n equals 1 over n, 1 over n, dot, 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 1 over n, and things like this? And when does this converge to the vector x, which is just all zeros, for example? Well, I can't actually just say this is true for all epsilon, right? There exists an n. I can't just use these vectors here unless I am bringing this back into the real numbers. What is very useful here is this notion of distance. The distance is associated to a norm, and the norm pops me out in the real numbers. So now I can start at saying, okay, I want the distance between x and xn to be going towards 0, the distance being the subtraction between these two vectors. Well, we might ask what norm we're working in. If we're working in the 2 norm, this is a little bit obnoxious to try and find the 2 norm of. Right? But if we're in the 1 norm, for example, let's say, for example, that we are in this, let's say that we are in, how many components do we want here? Let's say we're in R4, something like this. So let's say that we're in R4 and we're asking for x sub n to approach to x. Well, the 1 norm here for this vector x sub n is going to be the sum of the absolute values of each of these values here. So 1 over n, 1 over n, 1 over n, 1 over n. So all told, this is going to be 4 over n when added all together. Now that I have this in terms of a real number, I can ask the question, does 4 over n go to 0 as n goes to infinity? Does it? Well, it sure does. It's 4 times 1 over n, and 1 over n goes to 0 as n goes to infinity. So in fact, we have that this would converge to 0 because we use the 1 norm here, we would say that it converges in the 1 norm in this space. And the reason that we want to be a bit picky here about why we're specifying the 1 norm is that we know now that the same vector space can have multiple different norms. But whenever we give a vector space, like in our problems and things like this, we will need to specify the norm if we are asking for convergence. So if we have a sequence converging to x, we need to ask for a norm because the distance function given here needs a norm to do it. And so we need to specify what that norm is. That norm could have been the 1 norm, but I could have done the infinity norm as well, couldn't I have? Because the infinity norm of this vector gives me what? 1 over n, and 1 over n converges to 0. It's not always the case that for every vector space, if something converges in 1 norm, it converges in the other one. So we want to be a little bit careful about what norm we're using when we do that. We'll say that a vector x is a good approximation of the vector x naught if distance of x naught is small. And this is useful, especially in approximation theory, and using this for any kinds of computer applications and things like this. You might be trying to get something within a machine epsilon, and if you ever need to do that, approximations are where it's at. Let's talk a little bit about what unit circles look like. I can see the unit circle inside of here somewhere, but I see a lot of other shapes here too. Here is my x and y axes, and I could see the unit circle in here, hidden in here somewhere, right? Because I know that the unit circle that I'm familiar with, at least in terms of the 2 norm, is given like this. It's given as, well, let's see, rather, I think I know it in terms of this, x squared plus y squared equals r squared. That's just the formula for a circle and things like this. In particular, anything on this circle would have a distance of 1 from the origin. That is with respect to the 2 norm. How do I know this? If I'm taking the unit circle here, then I know that this is going to be of length 1, so my radius is going to be 1. So I'm going to be taking the square root of x squared plus y squared to equal 1 here. Well, the square root of x squared plus y squared, this is the x norm of the 2 norm of the vector x, where the vector x is given by the vector xy. So this is known as the unit circle for the 2 norm. So this is the 2 norm unit circle. So you can see here in our first bullet point, the norm of x equals x1 squared plus x2 squared, taking x and y. So this is x squared plus y squared to the 1/2 power. This is going to be indeed the black circle here. But there are different unit circles for each different norm. For example, what if I had taken the norm and actually multiplied the first component, the x component, by 1/2? Now what would I have to do? What would I have to do for x, for example, in order to get something on that works for the 2 norm? For example, if I had that the norm of x, I was looking for all values where the norm of x is equal 1. This is known as the unit circle for the norm, whatever norm it is that I'm given. And let's say that this norm is this, then how would I get it to be the case that the square root of 1/2 x1 squared plus x2 squared equals 1? Well, let's say that x2 equals 0 for now, because that can at least give us some answers. Then we'd be looking at values where the square root of 1/2 x1 squared equals 1, and that could get us where x1 squared equals 2. So x1 is equal to plus or minus the square root of 2. So I know that on this circle, plus or minus the square root of 2, comma 0 should be 2 points on this unit circle. So these should be 2 points on here. Can I see 2 points like that? Well, here's 1, 0. Here's -1, 0. And here I have some points all the way out here on this side. And if I go through and check what that is, indeed, this is the green oval kind of thing, more of an ellipse, maybe better to say. Because what we've done is essentially we've multiplied x1 by 1/2. So x1 has to work harder in order to get, or has to be longer, maybe better to say, in order to get to the edge of where the length is equal to 1. So it has to work a little bit harder to get there. In terms of x2, on the other hand, there's no scalar there, so it just stays at around the same spot as the unit circle did. So here we have 2 points for this unit circle. But we could have gone farther. The question that we're trying to answer here is, what are all of the points in the xy plane such that the norm of that point equals 1? Let's take a look at this next one. Let's take a look at the norm of x equals the magnitude of x1 plus the magnitude of x2. That's the 1 norm, remember? We already have one vector that has one norm of 1. We remember that's the 1 norm of 1/2 comma 1/2, that this one is 1. And remember, we were saying that that's kind of a weird one because that seems to be a strange calculation if we're trying to say something has a distance of 1. But in the 1 norm, that is the distance from 0 that we're talking about. Well, where would 1/2 1/2 be? It should be right over here, right? And indeed, you can see how this unit circle works is that as my y decreases, my x increases, and the relationship between the two is very linear. It's a very linear relationship. If this had to be if this got subtracted by some epsilon, then this would have to be added. The same epsilon would have to be added to the y component in order for this to still equal 1. So because of this, this diamond right here ends up being the unit circle for the 1 norm. So that's the one in blue. What do we think the unit circle is for the max? Remember, this is the one that takes the maximum of any one element. So for example, 1, 0's length is 1. 0, 1's length is 1 because it's taking the maximum of those two. But what about 1, 1? What is going to be the infinity norm of 1, 1 here? Well, it's going to be 1 because it's taking the maximum of 1 and 1, which is just 1. That's this point all the way out here. Notice that the way that this one works is very square. If you have that y is equal to 1, which is what you have on this line, then you automatically know that your length is going to be at most 1 as long as x is in between -1 and 1, because y is bigger in absolute value than x in that space. So because of that, this square ends up being the unit circle in the infinity norm. So here we've gone through a few of the norms: 2 norm, 1 norm, infinity norm. This one doesn't have a name. It was just one to use as an example. So now we've talked about unit circles with respect to each of these different norms. Let's go ahead and see some norms with respect to different examples as well, not just in terms of Rn, but in terms of functional spaces too. Let's take a look at V equals the continuous functions on the closed interval going from A to B. Here is the uniform norm. This one is called the uniform norm. It is f sub infinity. And what it is that it's the maximum value of our continuous function on the interval from A to B. For this, technically, we need to say that a maximum value exists because our norm can't be infinity, but we know this thanks to the existence of an absolute max and absolute min on closed intervals for continuous functions. This is called the uniform norm, by the way, because if you get that a sequence of functions converges to 0 in this particular norm, you would have the sequence converging uniformly. So that's the reason for that name right there. And then we have what is the 1 norm for functions. Some might call this the L1 norm for functions, which is the integral of the absolute value of the function f on this space. Now, because we are on a continuous functions on a closed interval, our function is bounded. So that means that this is going to be finite, which is important for us. We cannot have infinity as a length. That doesn't work. But this norm still satisfies the other important things. One, it's always positive. This is why we have absolute value right here. If we didn't have absolute value, this integral could have been negative, and we do not have a well-defined distance of length because we have something negative there instead. But this does work with, if you put a scalar multiple times a function, you can just bring the scalar outside. Because of that, it works well with homogeneity. And then finally, it is going to work well with the triangle inequality because the fact that the triangle inequality works well for functions as well. Namely, the absolute value of f plus g is the absolute value of f, or less than or equal to the absolute value of f, plus the absolute value of g. And this 1 norm is an example of kind of like the 1 norm that we had in terms of Rn, where you have the absolute value here, which is kind of like raising to the 1 power. And then once you've taken the integral, you still raise to the 1 over 1 power, which is just itself. That generalizes for any p being greater than 0. So you can define what is this p norm, only a norm for p greater than or equal to 1. Otherwise, it's a semi-norm. And to be taking the absolute value of f of x, raising it to the p power, then integrating, and then raising to the 1 over p power. This ends up being a norm as well, very much thanks to the same sort of work as Minkowski. All right, so some neat things here, really. So let me give you, my apologies, had to sneeze there. You could do this sort of setup here for any of these p greater than or equal to 1 and work very similarly to how we did things in the norm on Rn. The reason I like to think of these things as very similar is that think about Rn, right, as kind of like an n-dimensional vector space. And what you do is you add up each of the components in each of those vectors, raise them to the power of n, and then you, not n, let's do it to p because we want to specify that. There we go. So x of n to the p, and then we take it to the pth root, right? And this is how we would do this in this way. Well, if we don't have n-dimensional, we're not finite dimensional, if we're infinite dimensional, say like in the continuous functions, then our sums no longer work very well. Instead, what we need to do is do what is an infinite sum. We need to do an integral of this function. And we have that the function works the very same way. We raise each component to the power of p. We sum everything together, just like we integrate here. And then we take it to the power of 1 over p. So these are very similar norms to how these things worked in terms of Rn. Let's keep going here and talk about the inner product. Now let's start with the real vector spaces because it turns out we have a very different definition for real vector spaces versus complex vector spaces. The reason being is that our understanding of length is very different. Remember how we had to take conjugates of certain values in our previous video? We're going to have to do something different there as well if we're looking at complex vector spaces. But let's start with real vector spaces too, and let's see if we can find anything that works very nicely here. The notion of inner product generalizes the notions of dot product of vectors inside of R3. So let's go ahead and see a definition. Let's take a function beta, which is going to be v cross v to r. So think about like the dot product, right? You had x dot y. What happened when you took the dot product of two vectors? You got a scalar number out. You got some value c. This is exactly the function that we're looking at here. We want this function to be well-defined going into the real numbers. We're usually going to call it like this. If you have two vectors inside of here and you use the little bracket notation on the ends, that will be what is known as the inner product on V. And we're going to ask for this to be positive, symmetric, bilinear. Positive means if you ever have two vectors inside of here, the same vectors, then it's non-negative, it's greater or equal to 0, and in fact equals 0 only for x equal to 0. That's positivity. We're also going to ask it to be symmetric. What does symmetric mean in this case? It means that we can switch these two vectors and get the same inner product for them. Just like here, x dot y was equal to y dot x. It did not matter the order that we took our dot product in. That's important because sometimes you can construct a particular function that satisfies everything else but does not work when you flip. We'll see that in our complex vector space examples. We want it to be linear in each variable. That's 3 and 4 put together. Namely, we want to be able to scale out this first component, bring the r outside. And then we also want to be able to add in this first component. We want to be able to add x. If we have x plus y comma z, we want to have xz and yz as each of their inner products individually as well. Now, why did we only talk about the first component? Is there something special about the first component here? There is not. Why did we only talk about the first component then? Because if I have something is true for the first component, what do I know about the second component? Well, let's say, for example, I'm working on x comma y, and I want to know something about what works with the second component. Well, I can use the fact that my inner product is symmetric and make the second component my first component. So if I want to work with the second component, well, I know it's the same as if I flip them around. I could make my y my first component and everything is still equal. So even for the second component, I can bring scalars outside. I can break up sums. I can do all of that sort of stuff, even with the second component. So that is interesting about real vector spaces here. An inner product space is going to be a vector space endowed with an inner product. Right, so that means that we're going to have to specify that inner product because, again, just like before, we may have a space that has more than one inner product on it, although this one will be much fewer and farther between. You can have multiple norms on a lot of spaces, but defining multiple inner products, while not impossible, is less of a likelihood. Let's take a look at some inner products here. One inner product for Rn, which one, by the way, has a lot of dot products here, can be this one. You can just take the dot product as normal, but you could also be weighting the dot product. Here's what I mean by the weighted dot product. You could take each product of the components of your two vectors, and you could be multiplying them together, and then after you're done multiplying them, multiply them by some fixed scalar that's written to the side, right? You have this dot product going on, and then for each component that you do, you have this d1 written over here to the side, and you multiply that first multiplication of the first components by d1. Then you have another scalar that multiplies times the product of the second two components all the way up to the nth components. As long as all of these are greater than 0, you get to retain your positivity, and that is good enough for us. In general, we could have even done this where we multiply both of the vectors x and y by an invertible matrix D before we keep going. By the way, this second point is a special case of this third point. We could have been considering the invertible matrix known as the diagonal matrix, which takes the D components that we were talking about before and raises each one to the 1/2. If this was our matrix D, then if we multiply dx, we would just get scaled components of x1 and scaled components of y1. And if you multiplied each of those scaled parts together, d1 to the 1/2 times d1 to the 1/2 is d1. So that would work. The reason we need invertibility here is that otherwise you might ruin positivity. You might have non-zero elements that multiply times this matrix to give you 0. The thing is that if you have an invertible matrix, you know its null space is going to be 0, just the vector 0. And because of that, we know that we have positivity. So for anything else, it would be non-zero. And so the dot product gets to take care of us the rest of the way. This one is very interesting, right? Lots of different dot products here because you can imagine a lot of different invertible n by n matrices. Here's another example. This time, instead of in terms of Rn, we could be using a dot product that is the trace of the product of two operators. Here's how we're going to do this one. We're going to take two matrices that are m by n matrices. So A is m by n, B is m by n. I can't multiply A and B together because A, remember, is an m by n matrix, as is B. But B transpose, on the other hand, is an n by m matrix. So I can take the product AB transpose. And that's exactly what we're going to take in here. Now, this is not yet going to be in our scalar field. This is not yet a real number. But if we take the trace, remember that the trace is the sum of the diagonal elements inside of this. If we take the sum of the diagonal elements, then that is going to give us here this trace. All right. Now, it turns out there is a formula for this, and it does involve the elements of our matrices. If we write A equals Aij, let's say that this has m rows and n columns, and we write B as Bij, again having m rows and n columns, it turns out to be a very nice way to write out this trace. First, after doing the product, you get a lot of common elements inside of there, but you want the common elements to all be on the diagonal. So if you go through and simplify that formula, you get the sum of just basically multiplying each of the corresponding elements together and summing them in terms of j and summing them in terms of m, or I, rather. This way, you kind of get, it's a little bit like a generalized dot product, right? Because we would do the same thing for dot products of vectors. Now you can consider this as like a dot product for matrices. If you do this, then now you have the space of n by n matrices as an inner product space. An inner product space because an inner product has been put on it. We could do this with functions as well. If we have the inner product of two functions and the continuous functions with closed intervals a and b, then we could be taking the dot product of two functions to be multiplying the functions by each other before integrating by a and b. So first things first, we multiply the two functions together, f and g, and we take a look at a and b here as well. A and b are going to be our endpoints of our space. So we're not just integrating a part of it, we're integrating the whole thing. And we can multiply these things together. Well, first of all, what happens if I look at, for example, the inner product of f with itself? I'll take the inner product with f itself, and I'm looking at the integral of going from a to b of f squared of x, or maybe I could better write it as f of x quantity squared dx. There we go. So there's the square. So I'm taking the integral of something like this. Well, notice that, first of all, this is indeed a positive operator. Why is this a positive inner product space? Or why is this a positive inner product? The reason is that f of x squared is also greater than or equal to 0. So when I integrate a non-negative function, what I'm going to get out is non-negative. In fact, if it's ever non-zero at a point, then an integral is going to catch that little bit of area that it has underneath there. So the whole integral will be greater than 0. So the only thing that makes 0 is if f is 0. So we can then go through and check that it has symmetry, f and g, g and f, doesn't matter the order and stuff like that in there. Scalars work very nicely in each variable. And finally, adding functions inside of here works nicely because of how the addition works with the integral operator. So this ends up being an integral or an inner product space as well, and a very interesting one at that. We've started figuring out a way to take inner products and put them on function spaces. This is our notion of dot product for the continuous functions. We could have even weighted it, just like we weighted the functions of the parts of Rn. We could have been weighting each point x by its own little bit using what is a weight function here. Here, we just need our weight function to be bounded, piecewise continuous, and positive. Positive because we don't want to just put w equals -1 and get a negative integral out for what we were just looking at before. So if it's bounded and piecewise continuous, then we're good to go. The piecewise continuity allows us to also be able to say that zero functions work very nicely with it. Okay. So bounded finally will get us to that it's not infinity everywhere, right? Or not infinity somewhere. That would be a little bit strange for us as well, because then we could start manipulating this to make it a infinite value if we would like, or at least just one that's very strange. W is the weight function for this inner product space. Let's use this now to start trying to get an understanding of what we're doing. Inner products are weird to us. We haven't seen inner products except for the dot product in a while. Some of us may not have ever seen it. I know from my personal experience, I did not see inner product until I came to this level. So I want us to take some time and think about what the inner product is doing. The inner product is essentially telling us a couple of things. What does the dot product do for us in Rn? Dot product tells us, it gives us a quantity that helps us find the angle between two vectors. For example, we know that if the dot product between two vectors is 0, then the two vectors are orthogonal to each other. They are at a right angle. This is kind of how we can be thinking about the inner product as well. They're in some sense telling us how much are the two functions in line with each other and how much are they going in opposite directions, and in what ways are these parallel or orthogonal, and in what measure is that true. Some way that I like to talk about vectors with my students in Calculus 3 is that if my angle between these is acute, then the cosine of the angle between them is positive, and hence the dot product between those two things would be greater than 0. So even if something is not exactly parallel with it, if you have something that has a positive dot product with another thing, you know at least it's going partly in that direction. Again, it's very confusing to be thinking about this in terms of things like our function spaces. Like, what does it mean for one function to be going in the direction of the other? In this particular instance, it means that the functions start aligning with each other. They're going in similar directions, and there's a very vague understanding of what that sort of thing means. So there's some notion of angle inside of here. The idea that's best understood here as a generalization of this is the dot product. So let's be thinking about the dot product while we go through this problem. Let's try and find an inner product on R2, which we know is spanned by E1 and E2, E1 being just 1, 0, and E2 being 0, 1. Let's take it so that the following inner products take place. We want the inner product of the first basis element with itself to just be 2. And we want the inner product of the second basis element with itself to be 3. And finally, we want the inner product of E1 and E2 to be negative 1. Why didn't we give a definition for E2 and E1? Why didn't we give a definition of the inner product of E2 with E1? I think you may have gotten it. That's because the inner product is symmetric, just like the dot product is. So this should also be negative 1. Just something to keep in mind there. Well, how would we do this? Well, we want to start by thinking of an inner product that works on all of R2. But the reason that I think that we have basis elements here and here is that any element inside of our space of R2 can be written as a linear combination of those things. Now, I want to start with two elements here, x and y. The reason is that inner products have to deal with two elements, x and y. So I'm going to take those two elements, x, which is x1, x2, y, which is y1 and y2, and I'm going to write them as linear combinations of E1 and E2, respectively. Let's ask the question about how we would define the inner product of x and y. Well, x and y can both be written in terms of their particular sums in each component of E1 and E2. What do we know about inner products? Well, just like dot products, you can break apart sums. That's exactly what we do right here. We break apart sums of these based off of the first component of x1, e1. So you can see that the x1, e1 becomes its own term, x2, e2 becomes its own term, and we can also take out scalars. We can take x1 out, we can take x2 out. Each one gets to come out outside of the inner product. Now remember that we said, although that we don't have a specific property associated to it, the second component here also has the same properties. You can break it apart thanks to sums and scalars, thanks to the fact that it's symmetric. Anything that works for the first has to also work for the second. And that's exactly what we get here in this next line. We can break apart this one into 2 and bring the y1 outside. That gives us this first term. We can, after having broken this apart, we can do the same thing with y2, e2, bring the y2 outside. Notice that the vectors that are left over here are now vectors we know the values of. We know the inner product of E1, E1. We know the inner product of E1, E2. We factored out all of the terms into each own inner product, and we have taken the scalars outside of the inner product. We can do the same thing with this inner product to get something like this. Okay, so this gives us what we're looking for here. Now we know the inner product of E1 with itself is 2 times x1, y1. This one, E1, E2, is -1. So we're going to plug in -1 here. We also know that E2, E1 is -1. So we'll plug that in here. And finally, 3x2, y2. We got that value there as well. Only thing to check is to make sure that this actually does work. The only thing that we have to check here, we automatically know, thanks to the properties that we've been using, that this should be symmetric, that this should be, it should scale well, have homogeneity, and it should be additive in each term. Now, the only thing we have to check left is positivity. Well, we already know it's going to be finite. We need to make sure, though, that for any x that's not 0, that this is greater than 0. So, but for this one, we get to check to see that every vector gets to be the same. So like x1, x and y are both the same vector in this particular scenario. Remember, we do not have to check that x comma y inner product is greater than 0 for all x and y. This is not what we have to do. Whenever we want to show positivity, it's only between the vector x and itself that we need to show that the inner product is positive. So let's go through and calculate it. We have the formula for everything we need here. So I just plug in, instead of y1, I plug in x1, and I get 2x1 squared. If I do have x1 and y2, then this is x1, x2, and then this is 2 times of that because this is x2, x1, because these are the same. And then I will have 3x2 squared right here. Question is that if x is not equal to 0, is this greater than 0? Only thing I'm concerned about here is this negative term. I'm not too sure about that here. So I have to think about that a little bit. Well, isn't there a way to rewrite this particular term here? Let's see if I can give myself some space to figure this out. Is there some way to rewrite this? How about if I rewrote it like this? I know that minus 2x1, x2 takes place usually in the middle of a binomial expansion. So I could write this as with an x1 squared up on top and an x2 squared right here. And if I rewrote all of this stuff, then this would be x1 minus x2 quantity squared. That's something that is definitely positive. Can I do that? Well, I have 2 x1 squareds here, so I could just give one of them over here and then just have the other one left over on the side. I have 3 copies of x2 squared, so I'm okay giving one over here to this binomial expansion, and I'd have 2 x2 squareds left over. And that gives me this formula right here. Everything here is squared, so if x is not equal to 0, that means something there is going to be not 0, either x1 or x2. And if that's the case, then this will be non-zero. That's good enough because now you're just adding things to it. So you've got something that is non-zero for sure. So this is an example of how we might use inner products on R2. By the way, if we tried to check this and we got that there was a non-zero vector that evaluated to be 0 when taking its inner product with itself, if we had gotten that, then we would have been forced to have said there is no inner product on R2 with this property. Just something to keep in mind. So let's take the inner product of a complex vector space now. All right, so this one's going to be slightly different. Again, the reason is that for complex numbers, there's a notion of conjugates that we need to make sure that we're keeping in mind. So let's take a complex vector space now. Complex vector space means that it works over C as our scalar field. Our scalar field is C. Notice now that our inner products are now allowed to be complex numbers too. So we're going to say that something is an inner product if it is positive and conjugate symmetric. Conjugate symmetric here means that it's going to be symmetric, but it's going to be with a twist. It's going to be a twist that's going to be taking the conjugate. It's also going to depend linearly on the first argument. That is, the first component is going to be linear, but the second component is going to be something called conjugate linear, and we'll see that in just a second. So for our first component, we need all the positivity stuff like the ones we've just been working with. Notice this conjugate symmetry. X comma y equals the conjugate of y comma x. This is because if we had just complex numbers inside of here and we tried to take the dot product of that vector with itself, we would get some imaginary and even negative numbers. Because of this, like for example, I'll go ahead and show you. For example, the inner product of I and I would be what? We take the dot product of I with itself and you get -1. That's less than 0. That's not going to fly. So what you do instead is you say that for this inner product, you're not going to take I and I, you're going to take I times negative I, the conjugate of this value. And I times negative I is equal to 1, greater or equal to 0. That's exactly what we want. Okay, then we want it to be linear in the first variable, so we want it to have all the same properties as the real vector space had. But in the second variable, it's not going to be linear anymore. Notice this. It's going to be dependence on the second argument where it is conjugate linear instead, right? The reason that this is true is that, remember before, we were able to just switch back the first and second parts of this inner product willy-nilly. We could just take x comma y to be equal to y comma x. Now we cannot do that. Whenever we switch, we do it at the cost of gaining a bar over our inner product. So for example, if I wanted to rewrite this with the ry plus sz on the left-hand side, I would get that this is ry plus sz comma x with a bar over it. Now with the bar over it, I could start extending linearly, but the bar remains. So I'm going to have r times yx, and then I'm going to have plus s times zx when I expand this out. Now, when I switch these back, the bar will go away from the vectors, but once I'm done, the bar will remain over the scalars because the x and y can flip back at the cost of adding another bar, but a bar of a bar, meaning taking the conjugate twice, is just going to get us back to the original element. And then s, this is going to give us xz. This s also gets a bar. So this is going to be conjugate linear in the second component, and the second argument, we'll call it, for inner products. And I'll call it argument from now on instead of component, because I want to distinguish it from a vector. This is not a vector here. These are two arguments being put together. Let's see some examples. We've already seen one. This is the dot product in the complex numbers to the nth power, so Cn. We can take the second vector to have a conjugate value in each of the things. So for example, the I and negative I that we saw before. So in general, if we want to check these things, we just need to check and see how it works with, say, the vector x taking its dot product with itself. At this point, what you have is x1, x1 bar, plus x2, x2 bar, plus all the way up to xn, xn bar. Now, this value is very special because remember that we said whenever you have something like a plus bi and you multiply it times a minus bi, what you get is a squared plus b squared. That is just a quick difference of squares there. The reason this is a plus instead of a minus is that you're multiplying times I in your second part. I squared is -1, so that negates the minus and makes it a positive. Well, this is just the length of a plus bi quantity squared. Because why? If you take a comma b as your vector, you get the square root of a squared plus b squared. This is the way of taking a length inside of the complex numbers. So this is the magnitude of this vector in the complex numbers. So this is exactly what you see here. x1 squared plus x2 squared plus xn squared and things like this. And that's because in this case, you have that all of these numbers are exactly the same. So this is just the length of x1, x2, xn. Okay. Also, you could take the conjugate value here as well. And if you take the conjugate of this, you're going to get, you can see a lot of bars, but as you keep stacking the bars on top of each other, you notice that the double bars for y1 come back to be nothing in terms of this, right? So this is just to say eventually that you get the conjugate of the magnitude of the inner product of xy to be the magnitude of yx. Essentially, the bars stack the way that they should. Okay, so we've gone through and checked the important things here. I think we can check that it is linear in the first variable, namely scalars can come out and that addition works nicely for this particular example. But there are more examples out there. There's the example of looking at vector spaces which are functional spaces. So this is, again, the continuous functions on the closed interval from a to b. But notice the difference. This little c right here means that it takes values in the complex numbers rather than just r. It takes values in the complex numbers rather than just r. So for example, you could consider the function f of x equals ix. That is valid now, right? Here, x, however, the closed interval from a to b is a real vector, is a real closed interval, but you could multiply them times I so that your values now take place in the complex numbers. You could do ix plus x. That also would work. This now has real and imaginary components. All of those would be valid inside of this vector space as terms as functions. Here's what we get for the inner products here. Notice that because of the fact of us having conjugate linear in our second component, what we're going to see is that our second component gets a conjugate over it whenever we try and define it. This is so that we retain the notion of conjugate linear for whatever our second argument is. For example, the inner product of f and g inside of this space will be the integral from a to b of f of x times the conjugate of g of x, the conjugate of g of x, right? And this is so that whenever you try and flip the roles of f and g, if you just flip the roles willy-nilly, it would not be the same function, or it would at least not be the inner product of g and f, because g is still the one that has the bar over it. But it would be if the conjugate of the inner product of g and f, because if you distributed that conjugate all the way through, the g would finally be non-conjugate and the f would gain a conjugate. So this would be the correct inner product for this. Same thing if you add a weight function, where this time we want the weight function to be bounded, piecewise continuous, and greater than 0 everywhere. So we just want the same stuff as what we had before. So these are both very good examples of inner products for functional vector spaces. Notice that we want these to be in the continuous functions, and we did this the previous time before, because again, we want these inner products to be finite. We don't want them to have an infinite value. That wouldn't make sense for us. That would violate the fact that these are functions from the vector field cross itself to either the real or complex numbers, because the real numbers don't include infinity. Complex numbers don't include infinity. So we stick ourselves inside of the continuous functions on a bounded interval so that all of these integrals end up being finite. They might be arbitrarily large, but at least they're finite. Let's talk a little bit about inner products and what they can do. So there's a lot of stuff going on with inner products, and some of it has a lot of very good correlates to what we saw in the real numbers. One of them is this one. Here is one about trying to figure out the difference between the inner product of x and y versus the magnitudes of x and y. You remember this one? Remember that we took the magnitude of x dot y, and we said that this was going to be equal to the magnitude of x times the magnitude of y times the cosine of the angle between them. Take a look at this formula. Take a look back at what this formula is, and notice that there's a lot of similarity here. Namely, it gets a little bit more clear once you remember that we said that whenever you have cosine of theta, this is something in between -1 and 1. So if you look at this in terms of absolute value and you erase the cosine of theta, then you get this inequality right here. This is something we talked about in our previous video. Now take a look at what we have over here. This is the magnitude, or the absolute value, better, of the inner product of x and y, quantity squared, so there's a squared here that's not over here, is less than or equal to the magnitude, or the inner product of x times the inner product of y with y. Well, what is the inner product of x and x? Remember that we can define this as a norm in terms of the dot product, and in fact, the way we should be thinking of this is as the norm squared. We should be thinking of this as the norm of x quantity squared. This is how we should be thinking of it. Same thing with the inner product of y with itself. We should be thinking of this as the norm of y squared. So really, there is a lot of similarity here. Here, we're replacing the inner product with the dot product, and then we're just squaring everything. If we do this, even in a general vector space, this is the idea of what we have. Now, the issue here is this. We do not have a nice definition of the dot product, like take the first x components and multiply them together, because we could be working in a function space. Our vector space is now abstract, so we do not get to use just the fact that, okay, we know what is going on inside of here to try and go through and prove this. Instead, we need to use the properties of an inner product, namely that you can scale, it's linear in the first variable, right? And then it has very nice properties. For example, these we know are greater than or equal to 0 and only 0 when x is 0. Same thing for y. We need to be going through and using these properties to try and go through and prove this. This proof is going to take a little bit of time, but I'm not going to dwell on it too heavily because I think we've already kind of gotten a good bit here. But this sort of proof technique is going to be important for us. So I want us to kind of walk through this a little bit. Let's start here. Let's define a function in terms of t. And what that function is going to be, it's going to plug in it's going to plug in a complex number, and what I'm going to get out is a vector. And what that vector is going to be is going to start at x. When t is 0, it's going to just be x. But whenever I add something to t, if I make it t of 1, then I'm going to add a component of y to my vector. So you should think of this way, right? You've got x right here, and then maybe y goes out this way. If I just imagine t going out in the, if I imagine t growing in the positive direction, then it's going to start from x and it's going to go toward y. Or rather, it's going to go toward x plus y. So it's going to go a little bit farther. Then it could go toward -1 as well, and then it can also be going in the complex plane. T could be I, for example, and we'll need that in a little bit. Question. This is a vector, right? So I can plug these into the inner product here, and I can ask the question, what is this inner product? Well, if I go through the calculations of this, it turns out that I get some sort of maybe expanded notion of what this looks like. Notice that I had to take out the t here with a bar on the side here, because sometimes I had to take the t out of the second argument. That's the reason for the bar there. Let's assume that y is not equal to 0, otherwise our function isn't doing very much at all. And let's choose a very special value for t, the negative of the following ratio, the ratio of xy to yy. Okay, so the ratio of xy to yy. By the way, you should be kind of thinking of this as a scalar projection, something that we talked about a little bit before. Although this time, to be fair, it is the negative scalar projection. But there's a very similar notion to what's going on there. Then the inner product of v of t with itself, now with this choice of t that I have plugged in, a lot is going to simplify. We can go through all of the work and things like this, but notice that's the inner product of x with x gets to stick around, and then a lot of other stuff ends up canceling very nicely. Namely, I'm only going to be left with the first and the third terms here. You can go through and check that yourself if you would like. Well, if I have something like this, then I can rewrite it a little bit. I have that this is t times the inner product of y with x. So I'm going to have, once I span this out, the negative of xy times yx. Well, what is this when I take the bar of it? This is negative xy with xy with a bar over it. Well, that's just going to be the magnitude of the inner product of xy, quantity squared. And all of that's going to be divided by the magnitude of yy. Hence, this expression inside of here. Notice that the magnitude of v sub t is greater than or equal to 0. This is by definition of inner product. By definition of inner product, we have that this automatically holds. Because any vector multiplied or inner product with itself is going to be greater than or equal to 0. So this is greater than or equal to 0. But guess what happens? When you go through and expand this out, the results might surprise you. What you get is exactly what we had up here. If you go through and, for example, add this to the other side and then multiply both sides by the inner product of y with itself, then you get the statement that's given over there. So namely, you get that the absolute value of the inner products of x and y, quantity squared, is less than or equal to the inner product of x and x times the inner product of y and y. In the case that y is 0, you get that x comma y is y comma y. In that case, you have y is 0. So really, these two things are the same for any t, in fact. So then you get x comma y is y comma y. And that's going to be 0 because y is 0. So that gives you a neat little showcase into the inner product there as well. So a neat little theorem there. We're going to connect this to something called the Cauchy-Schwarz inequality. That's going to be our big deal here. But really, this is the Cauchy-Schwarz inequality. This is the proof behind this theorem. The way we're going to use it is just by taking square roots of everything. We're going to take square roots of all of these different parts, and we're going to have something like this. Again, you can think of this as like the absolute value of the dot product is less than or equal to the magnitudes of x and y, respectively. A lot of corollaries come from this. In particular, because now we can do this with any inner product, not just an abstract one. Any inner product that we'd like to use works neatly for here. In particular, we know for the dot product that it follows from this theorem that the absolute value of the dot product is less than or equal to the lengths of x and y multiplied together. So equivalently, we get these formulas that work very nicely for us because we can be working on these in Rn. So this is the formula for the dot product and the lengths written down on this line down underneath. But what's really interesting is that now we have some things to say about functions. Getting inequalities in this particular world is a huge deal for us because it allows us to approximate or say this can't go beyond this, which is amazing for our proofs. So for example, if I take the inner product of f and g like I saw with C of AB, notably not in the complex numbers for its values, but in the real values, then the inner product of f and g, which is what this is, the integral from a to b of f times g, squared, that's because of the previous theorem, is less than or equal to the square root of the inner product of f with itself, but squared again because this was squared, so these cancel out. It's the inner product of f and f. Well, the inner product of f and f is just f of x quantity squared, and this is going to be g of x quantity squared. So that's where we're plugging in a particular inner product, the inner products that we were given for these continuous functions. Now, I kind of spoiled the game a little bit to try and help us understand what the Cauchy-Schwarz inequality was coming from. But this is a norm. The square root of the inner product is a norm. Even if I'm not on a normed space, this is important. Even if I'm not on a normed space, if I have an inner product on my space, I can put a norm on my space. And that norm is just going to be the square root of the inner product. So think of this as like the square root of the dot product, right? In terms of R2, this is the square root of x1 squared plus all the way up to xn squared. So this is exactly what's being meant here. We can check and make sure that everything here works neatly as a norm should. Positivity, homogeneity, things like this. The triangle inequality is going to come from Cauchy-Schwarz. So we had to prove Cauchy-Schwarz before we could have used this. Cauchy-Schwarz, remember, is the one that says that I can take the absolute value of x minus y and get that that's less than or equal to the norm of x times the norm of y. Okay, so that is this formula right here. So this gives us everything that we need. Some neat little proofs here to show that inner products give us norms. Amazing stuff there. Another neat little thing here in this proof that I'll go through and illustrate. I'll let you kind of work through the rest of it by yourself. But I want to illustrate this one right here. Is that these two things combine in this way. Here, we are not assuming that we are in a real vector space. We are in a complex vector space. And that is the reason for this RE to come out. So for example, the real part of A plus BI would just be A for any real numbers A and B. The real part is what's being done here. So in terms of a real vector space, this would just be x comma y plus y comma x as its inner products. You just flip the two around, you add them together. This is just 2 times xy. So this follows automatically. You can just take an absolute value at the cost of less than or equal to. But in terms of the complex vector spaces, what you get when you flip this around, remember, is you get x plus y, x comma y, plus the conjugate of x comma y. So if this is a plus bi, then this is actually a minus bi. Notice that you're only left with the real part, though, because the imaginary parts are going to cancel out. So you're left with 2 times a here. So this is going to be 2 times the real part of x and y. So that's where this part comes from. Again, you'd get the same thing. This is also less than or equal to 2 times the magnitude of the inner product of x and y by the fact that you're just considering the real part. The absolute value would consider the imaginary part as well and take the length of that vector, which would be longer than just the real part. Okay, very good there. Talking a little bit about norms induced by these inner products. So in Rn, for example, we've got our notions of length, we've got our notions of norm as before. We can also define the 2 norm based off of our inner product. Remember our inner product here being that this is the inner product of going from a to b of f of x, g of x, dx. This was our norm on the vector space C of AB. So if I want to, or our inner product rather, I should say. So if I want to define the norm, the 2 norm, in fact, then I would say that that is the square root of the inner product of f with itself. If I do that, then I get exactly this formula. All right. And this even works even if I'm working now in the complex vector space, because now I just get this. And now what I'm working with is f of x times the conjugate of f of x. And this evaluates to be the magnitude or the absolute value of f of x squared. So this is why, so this works even inside of this space with a C right here, with the complex numbers, this works as well. So this norm so the way that we will say this is that the norm f sub 2, this norm given here, on the vector-based space CAB is induced by the inner product given right here. It is induced by that inner product. The inner product came first, and then we defined the norm based on the way that you can always get a norm from an inner product, right? So the way to think of this is that inner product spaces are a subset of the normed vector spaces. Because for any inner product space, you can get a norm on it. So any inner product space is automatically a normed vector space. You just define the norm that is induced in this way. Okay? And finally, let's go through and discuss the angle and a few theorems that are related to this. Let's discuss the angle between two vectors in an abstract vector space. Here we have, since this is true, remember, think of this as like our dot product is in magnitude is less than or equal to the norm of x, norm of y. We can define the angle in a very similar way to how we would define the dot product between two things. We would say that the angle between x and y, notice our new notation here, this is our angle notation. The angle between the vectors x and y in our vector space is the arc cosine, so the cosine inverse of the inner product of x and y divided by the magnitudes of x and y. Note that this is only well defined because of this. Otherwise, we'd be trying to take cosine inverse of something greater than 1 or less than -1, and that wouldn't work very well. So we get our same formula as we did for our formula for our dot product. Again, for this, do be thinking about the dot product of x and y is the norm of x, the length of y, times the cosine of the angle between them. In particular, what happens when the dot product is 0? The angle between them is 90 degrees. Or we would just say that the vector is orthogonal. We would say the vector is orthogonal whenever the dot product between these, or inner product, better to say, is 0. This only works in a real vector space, by the way. The reason is that sometimes this inner product in complex vector spaces is complex. And so taking the cosine inverse of something like that would not work very well. Cosine only lives in between -1 and 1. But we can still define the notion of orthogonality. And in fact, we'll use orthogonality more than we'll use the angle. Orthogonality will make more sense to us than just the angle of it. So if we say that the dot product between two vectors is 0, we mean to say that those two are orthogonal. So you might be familiar with orthogonal bases and things like this for linear algebra. That's stuff that we'll definitely be factoring in at this point. Let's go through a few more theorems here having to do with these inner products and norms on them. So for here, we're always going to be letting V be an inner product space. And then what's to come, V is an inner product space. This stuff is not necessarily true in other places. And by the Pythagorean law, if x and y are orthogonal, that means in particular, right? Remember, this means that the dot product between them is 0. Then the length of x plus y quantity squared is the length of x squared plus the length of y squared. Well, why does this make sense? Take a look at our picture. X plus y is the length of the hypotenuse. X is the length of one side. Y is the length of the other side of this triangle. So this is the Pythagorean theorem, but this time we're looking at triangles in an abstract vector space. Did you ever think you'd be doing this? I'm not sure I would. So the proof of this is extremely nice because we know how the norm is defined in an inner product space. The norm is x plus y quantity squared equals the inner product of x plus y with itself. Notice that this is where the square is coming in, because now we can just write it as the inner product without having to worry about the square root. The square root is not here. Well, we can extend this linearly. If we do that, then we're going to have something like this. We're going to have x comma x plus xy plus yx plus yy. Well, regardless of whether I'm working in a real or a complex vector space, this is 0 and this is 0. Even if I have to do a conjugate linear thing for the second one, the conjugate of 0 is still 0. So both of these go to 0 now. So all I'm left with is the first and fourth terms, which evaluate to be the lengths of each of the individual sides. Crazy, because we have just done the Pythagorean theorem in an inner product space. It's a pretty cool thing. Another thing that we get a lot of inside of our inner product spaces are parallelograms. Take a look at these pictures right here. Remember, in terms of Rn, the way that we could solve for particular quantities, like the length of xy, for example, is to take a look at triangles that are put in these sides. So, for example, we could use the law of cosines here to find the length of x plus y quantity squared. What would it be? It would be the length of x squared plus the length of y squared minus 2 magnitude of x, magnitude of y, and the cosine of the angle between the two vectors, right? So we could find the length of x plus y there. What about the length of x minus y? Well, we could do the same thing, but we could use this triangle right here. This time, the angle between them is this one, whereas before, the angle between them was this. Do you notice that these two angles add to be 180? In that case, the cosine of the angle between them, if we call this one in particular theta, then the formula for x minus y quantity squared, this length here, is going to be the exact same as before. But instead of having this be cosine of theta, we're now going to be looking at, this was an obtuse angle. This is going to be an acute angle directly opposite from cosine. So the value of this phi, cosine phi wise, is going to be negative the value of cosine of theta. So we're just going to go ahead and plug that in. We're going to make this plus the magnitude of x times the magnitude of y times the cosine of theta. Notice that the minus and the plus would cancel each other out if we added these together. And if you add them together, you get the parallelogram identity. So this is the parallelogram identity. It is saying that the sum of the squares of the lengths of the diagonals of the parallelogram is equal to twice the sum of the squares of the sides of the parallelogram. Neat little fact here, a little bit of trick for us to kind of get us started. Here's a proof for it. We can do this now, even in terms of looking at things in terms of the abstract vector spaces rather than just in terms of Rn. And the proof is not the same as the one I just gave because we don't quite have a law of cosines, but we do have things that are very similar, namely linearity and the inner product. So we're just going to go through and use that. The norm of x plus y squared, for example, breaks up into all of these particular pieces. Norm of x minus y quantity squared breaks up into all of these pieces. If I add them together, the same sort of thing cancels, and I'm just left with the norm of x squared, norm of y squared, all multiplied times 2. Neat little parallelogram law for us there. Moving forward with parallelograms. We've seen triangles, we've seen parallelograms, we've got tons of shapes now in abstract vector spaces. Hard to think of this when you're thinking of functions, but it is a pretty interesting concept nonetheless. This theorem is actually really neat and is a little bit detailed in its proof, but a norm on a vector space is induced by an inner product if and only if the parallelogram identity holds for this norm. This one, by the way, is saying, for example, this is working with V being a normed vector space for just a second here. This is just for this theorem. Let's say that you have a normed vector space, okay? And let's say that you've shown that this particular norm has the parallelogram identity. Well, what you know is that your normed vector space is an inner product space. You just have to find where that inner product is, okay? So that's interesting. It says that if you have a normed vector space such that for all vectors, x and y, the following thing is true, then you know that your normed vector space is actually an inner product space for some inner product. And that when you induce a norm from that inner product, you get exactly the norm you started out with. So that's an interesting theorem that it tells us when a normed vector space can be an inner product space, is to check and see if the parallelogram identity holds for it. Then there's another theorem that says, suppose that you have an inner product space with an inner product given by the little brackets here and an induced norm. Then if V is a real vector space, there's a neat way to get the inner product of it from the norms. So this would actually be useful for us in terms of theorem 1, right? Because if in theorem 1, I don't know what this is, but I do know what this is, then I can define the inner product to be like this. This is the idea behind the polarization identity. The polarization identity says, I know that whenever I have an inner product space, then I can define the inner product just the same way by looking at the norms that induces by it and by looking at this expression, 1/4 times the magnitude of x plus y quantity squared minus the magnitude of x minus y quantity squared. If I don't know the inner product, then this is the inner product. I've just found out what it is. So the polarization identity is very neat in that regard. If it's complex, you got to add a couple of extra terms, and the reason being that you have a little bit more basis work to be kind of going through. Right? You have some things that are going off in the I directions as well for your inner products. So because of this, you need to add to your previous expression I times the magnitude of x plus iy quantity squared minus I times the magnitude of x minus iy quantity squared. So these are the identities and things like this that help us connect normed vector spaces back to inner product spaces. Again, inner product spaces are normed vector spaces, but not all normed vector spaces are inner product spaces. The only time that a normed vector space is an inner product space is if the norm happens to satisfy what is known as the parallelogram identity. All right? But that'll do it for us today. We've been discussing a little bit about norms and inner products and how they work within particular spaces in terms of real and complex versions. We've seen things like the Cauchy-Schwarz inequality, Pythagorean law, as well as the parallelogram law to help us get an understanding of what shapes look like in these spaces. So we've been talking about geometry, so we have some notion of what this stuff looks like. But it turns out when you have a norm or an inner product, you can talk about this geometry a whole lot more. Right. And so the notions of orthogonal, norm, and inner product are going to be huge for us coming forward. But that will do it for us today. Thank you so much. Have a wonderful day.